bit different with L'Hopital's rule. So let's look at this example. Okay, so in this example, so again, this is a L'Hopital's rule question, although, it doesn't look like that right away. So it's this funky looking exponent. So let's approach this limit how we do any other limit. What do? We directly substitute the number, right? So direct substitution of x equals 0 gives, all right, let's see what it gives. So we get 1 minus 1 plus 0 plus 1 all to the power 1 over 0. And so how can I write that? So 1 over 0 you should think of as what in this case, in this context? You should think of 1 over 0 as infinity. That's right. So this looks like 1 to the infinity. Okay, how do we deal with 1 to the infinity? Very briefly, what do we do? Kevin says ln. Good. I mean, that's the quickest way you can say what you do, right? We want to use L'Hopital's rule. Noam says get a quotient. Kevin says use ln, right? So those are both correct answers, right? I want to use L'Hopital's rule, but L'Hopital's rule only works for a quotient. So I need to get it into the form of a quotient, as Noam suggests. But how do I do that? So what Kevin said, I'm going to use logarithms to get the exponent into the form of a quotient. So use L'Hopital's rule, but first use logs, get quotient. Okay, so let's let L equal this whole big limit. Okay, good. Now I take the ln of both sides. Right, and then we know what to do from this point, right? The exponent now comes outside as a coefficient, and I can write 1 over x immediately as a quotient. So using my rules of logarithms, I can now write my limit as, let's see, ln of this whole big expression and then the 1 over x comes outside as a coefficient, which I will immediately write into the denominator, right? The whole thing is really times 1 over x, so the x just goes right in the denominator. Okay, good. Now we know that if we started with 1 to the infinity and I use logarithms properly, I should get either 0 over 0 or infinity over infinity, right? If I did everything correctly. But let's just make sure of that. So direct substitution of x equals 0 gives us, so double check, this whole expression I know just equals 1 if I substitute x equals 0. So I get ln of 1, which is 0, and the x in the denominator also gives me 0. So in fact, I do have 0 over 0. So now I can use L'Hopital's rule. All right, so we differentiate the numerator and denominator separately. Now the nice thing in this problem is the denominator being x, that means that denominator derivative will just be 1. So that kind of simplifies things a lot. So this whole thing is all going to be over 1. And so what is the derivative of the top? Well, it's going to be 1 over whatever was already there. Times the derivative of the inside function by the chain rule. And so that when I multiply by the derivative of the inside, that just multiplies the numerator of that. So I can write here the derivative of the inside, which is e to the 5x minus 3 times e to the 3x plus 7 minus sine x. So that is the derivative of that whole entire fraction. The nice thing is because the denominator of the whole complex fraction is 1, I know I'm not going to get 0 over 0. So in fact, I can already just substitute x equals 0. And what do I get? I get 5 minus 3 plus 7 minus 0 over 1 minus 1 plus 0 plus 1. And the whole thing is, all over 1. And so what does this give me? This gives us um, 10. 5 plus 7 is 12 minus 3 is actually 9. Sorry, not 10. Okay, and then finally, now we do the very last step. So all we have shown is that the log of my limit, so ln of L equals 9. So the limit I actually want, which is L, is e to the 9 power. Okay, we have about a minute left. So any last questions about this? How did you get 5 e to the 5x? So what is the derivative of e to the 5x? That derivative is 5 e to the 5x. Remember, that's from chain rule.